Welcome to Astronomy Daily, the podcast, where the cosmos comes into clearer view with each episode. Today, we'll delve into a selection of compelling stories shaking up the space sector. We'll discuss the Angara A-5 rocket's liftoff at the third attempt, an event that marks a significant moment for Russia amidst its recent space challenges. We'll also examine the sudden and mystifying shutdown of NASA's planet-hunting TESS satellite, pondering the implications of this unexpected hiccup in our search for exoplanets. Moving beyond Earth and its orbit, we'll explore innovative strategies to mitigate the ever-growing issue of orbital debris, an invisible threat to our sustained ventures into space. We'll then turn back the cosmic clock, investigating the fascinating research using crater analysis to uncover the ancient stories of moons orbiting our solar system's giant planets. And looking to future celestial encounters, we'll give you a sneak peek at ESA's advanced preparations for the JUICE mission's flyby of Jupiter's enigmatic moon, Callisto. Stay with us as we embark on this astronomical journey, unwrapping the secrets of the universe and bringing the latest in space exploration and technology straight to your ears.
The Astronomy Daily podcast.
Turning our gaze to the skies above the Russian Far East, the Angara A-5 rocket, Russia's aerospace hope, roared into the cosmos from the Vostochny Cosmodrome on its third scheduled launch attempt. After two scrubs due to pressing issues with a pressurizing system and the engine control mechanism. The launch's success echoed as a definitive statement of the nation's resiliency in spacefaring pursuits. This milestone for the Angara A-5, a behemoth engineered to dispatch heavy payloads into low Earth orbit, marks a pivotal stride in a sequence of rigorous testing needed to assert its reliability. The unveiling journey wasn't without its qualms, as the Russian space agency Roscosmos aired the Endeavour live, capturing the booster ascending to an altitude of 268 kilometers within the first 13 minutes. What we witnessed was not just the rocket's fiery departure, but also the manifestation of a long-haul commitment. It's a path strewn with setbacks, including last year's ill-fated lunar lander, which met with the lunar surface with an impact rather than with the soft landing planned. Development of the Angara A-5 has been painstaking, with a timeline punctuated by delays and spanning a decade riddled with only 3 prior liftoffs, one of which did not reach full fruition. Now, the successful deployment of a test payload casts favourable light on the prospect of Moscow's ambition, a new bastion in orbit to rival the legacy of the International Space Station. The implications run deep. The prolific Angara A-5 is charting the course to elevate Russia's galactic blueprint, foreseeably playing a role in delivering the foundational blocks for a forthcoming orbital platform. As we consider this recent flight, we ponder not just the engineering triumph and the fiery spectacle of launch. We look toward an era where resoluteness and innovation may lead Roscosmos to new celestial frontiers, the saga of Angara A-5 becoming a crown jewel in their cosmic odyssey. The cosmos has its mysteries, and one of NASA's key tools in uncovering them has hit a minor snag. The Transiting Exoplanet Survey satellite, known as TESS, has temporarily paused its vigilant search of the heavens due to an unexpected shift into safe mode. It's an unexpected twist in the mission's otherwise smooth journey since SpaceX lofted it to the stars in 2018. As NASA's frontline planet hunter, TESS has the vital job of scouting the skies for exoplanets, orbiting distant stars, seeking worlds that resemble our own Earth. The temporary shutdown occurred as TESS was performing routine operations, a hiccup in outer space that NASA's team is investigating to restore full functionality in the immediate future. Despite this pause, TESS, our cosmic sentry, remains in good health, poised to re-engage in its stellar census, taking duties shortly. What makes TESS's work so fascinating is its quest for planets that could potentially host life, building on the legacy of its predecessor, the renowned Kepler telescope. With a gaze that spans an area of the sky over 400 times larger than that watched by Kepler, TESS has been instrumental in identifying over 2,400 candidate exoplanets, including a pair of super-Earths, a mere 33 light-years away. During its mission, TESS has even contributed unexpected bonuses beyond its primary purpose. It caught sight of a brilliant gamma-ray burst, the violent birth throes of a black hole, highlighting the satellite's versatile role in our understanding of the universe. The temporary shutdown has certainly introduced suspense into TESS's narrative, a reminder of the fragility and complexity entailed in our explorations of the cosmos. Yet, its track record, a treasury of knowledge about distant planets and the grandeur of space-time events, assures us that TESS is more than a mere machine. It's a bridge to the vast potential of human discovery, a searchlight in the dark, charting paths to new worlds and universal secrets hitherto beyond our grasp. And so, we await with eager anticipation the reawakening of TESS to continue its grand survey of the galactic seas, sailing once more under the banner of curiosity and wonder. As we venture deeper into the cosmos, the issue of space debris becomes more pressing. Today, let's discuss some groundbreaking methods being put into practice to curb this growing concern, particularly concerning satellite re-entry designs. Engineers and scientists are keenly aware that the remnants of our endeavours circling the Earth pose risks both in space and upon re-entry. At the University of Stuttgart's High Enthalpy Flow Diagnostics Group, remarkable tests are unfolding. Here, a reaction wheel, a device pivotal for adjusting satellites' orientation, faces a rigorous trial within a plasma wind tunnel. This tunnel replicates the severe heat and speed of atmospheric re-entry, while the wheel itself is rotated, simulating the chaotic return journey of a satellite. Collins Aerospace in Germany has been at the forefront of these endeavours, making significant amendments to their Teldix reaction wheel. Their aim? To enhance what's known as its demisability, a term coined for ensuring the satellite can disintegrate in a controlled manner during re-entry, thereby eliminating the possibility of space junk surviving its earthbound descent. This innovative approach to design for demise, or D4D, was the focal point of this year's Space Mechanisms workshop at the European Space Agency's ESTEC Technical Centre. This gathering, which brought together a constellation of over 130 industry and academic experts, zeroed in on the urgency to perfect satellite mechanisms that vanish completely upon re-entering our atmosphere. The consequences of neglecting such technologies are stark, conjuring memories of past incidents where falling debris has come perilously close to causing casualties. It's imperative, therefore, that we consider either guiding the satellite fragments to ensure a reduced ground footprint or ensuring total disintegration where possible. New initiatives are already in motion. ESA and other industry heavyweights are developing spacecraft with the express purpose of capturing and safely deorbiting defunct satellites. This proactive stance underscores how essential specialized mechanisms will be in maintaining the long-term sustainability of our orbital environments. As the frequency of satellite launches grows, it's ever important to adhere to stringent debris mitigation regulations. The safety of our increasingly busy skies isn't just a matter of outer space. It's about protecting the blue skies of our home planet as well.
The Astronomy Daily Podcast.
The dating of moons within our solar system is an intricate puzzle that scientists are continuously striving to piece together. As the celestial dance of moons around Jupiter, Saturn, Uranus and Neptune carries on, researchers look to the time-etched surfaces of these moons to unravel secrets of their age and origin. At the core of this research is the technique known as crater analysis. The craters that spangle the moonscapes are not merely features for stunning visuals, but act as historical records. By counting these impact craters, scientists can estimate the age of the moon's surfaces. In the early solar system, a frenetic ballet of cosmic debris created a tempestuous environment. When Neptune flung planetesimals through the solar system, it set off a chain reaction of bombardments, the evidence of which is clearest on the outer moons. A recent study spearheaded by William Botka from the Southwest Research Institute has made headway in dating the surfaces of 26 moons. Through meticulous modelling of bombardment frequencies and their resulting craters, the team aims to understand the timeline of impacts and the resultant reshaping of these celestial bodies. Their findings tell a tale of obliteration and rebirth. Early massive impacts have vanished, lost to subsequent extensive resurfacing processes. For instance, on moons like Iapetus and Oberon, we see surfaces that were formed only a few million years into the onslaught of interplanetary collisions. Larger moons present even younger skins, masquerading the true extent of their ancient scars. This research illuminates and endorses the prevailing theory that larger moons likely coalesced from circumplanetary disks, akin to smaller-scale planetary systems. Yet, the absence of evidence from the tumultuous infancy of the solar system means a piece of the puzzle remains elusive. In pursuit of these enigmatic origins, future space missions equipped with advanced instruments are set to cast further light upon these distant realms. By harnessing gravity measurements and continuing the laborious task of crater counting, we hope to peel back layers of cosmic history to a time shortly after the dawn of our solar system. In this endless journey through time and space, each crater holds the potential to unlock chapters of a narrative that spans billions of years beneath the silent gaze of those celestial sentinels, our solar system's moons. As we journey 7 years into the future, the European Space Agency's JUICE mission orbits into our conversation. Now, envisage the year 2031. A spacecraft named JUICE soars past Jupiter's moon, Callisto, a spectacle that promises to unveil the secrets of this cratered alien landscape. Teams tucked away at ESA's mission control have already set this celestial dance into motion, despite it being years ahead of us. Picture this. Operators, with their minds cast far across the solar system, maneuver a terrestrial replica of JUICE, an engineering model here on Earth. They simulate the actions JUICE will take millions of kilometers away, testing its autonomous navigation software to perfection. This preparation is crucial, as the immense distance to the Jupiter system means there's no time for a real-time intervention from ground control. Think of Callisto, this sphere of mystery floating in JUICE's path. With the vast communication delay, the JUICE probe must rely on its eyes and brain to lock its instruments onto features on Callisto, rotate, and maintain a pointed gaze, all autonomously. This would entail the spacecraft detecting where Callisto appears before it, identifying its surface landmarks, and adjusting its position accordingly to keep its sensors trained on them, all while slicing past at tremendous speeds. This isn't just a matter of sophisticated programming, though. It's about preparing for scenarios where the difference between monumental discovery and a fruitless pass could hinge on fractions of a degree. The ESA team's meticulous planning and execution must also ensure that during this delicate operation, nothing is left to chance. In this instance, it's not hyperbole to say that ESA's mission specialists are rehearsing a ballet of cosmic proportions, where every spin, every leap, every arc must be orchestrated without the conductor's baton. So, when the day arrives for JUICE to embrace Callisto's gravitational pull, we, back on Earth, can hope to receive a trophy of scientific insights that have been years in the making. And that, esteemed listeners, is how the future of space exploration is meticulously charted from the confines of our blue planet. As we draw to a close on today's journey through the cosmos, I want to take a moment to extend a heartfelt thank you for joining us here at Astronomy Daily, the podcast. Your curiosity and passion for the stars and beyond make this exploration through the universe all the more exciting. If you're thirsty for more stellar content, I invite you to visit our website at astronomydaily.io. There, you'll find a treasure trove of past episodes, ripe for binging and bursting with astronomical wonders. Go ahead, dive into the archive and relive the highlights or catch up on what you've missed. While you're there, don't miss out on the opportunity to subscribe to our free daily newsletter. It's your personal briefing on the latest happenings in space and astronomy, delivered right to your inbox. Be the first to know about breakthroughs, sightings, and cosmic events. And for those who like to keep their finger on the pulse of the social universe, follow us on X, previously known as Twitter. Just search for Astro Daily Pod and make sure to hit that follow button to stay connected with the community of celestial enthusiasts. Thank you again for tuning in, and until next time, keep your eyes to the skies and your mind wide open to the wonders above. Clear skies and Godspeed. This is your host, Charlie, signing off.
The Astronomy Daily Podcast.